Hello, welcome to this tutorial on recursive least squares filters. In adaptive filtering and signal processing, the RLS algorithm is a powerful tool that dynamically adjusts filter coefficients to minimize errors, especially in time-varying environments. The RLS algorithm excels in providing faster convergence and superior accuracy when compared to other adaptive filters like least mean squares, especially when input signals are correlated or when rapid changes in the systems are expected. The purpose of this tutorial is to explore the key concepts of the RLS algorithm in depth, starting from basic principles to its step-by-step development and ending with practical demonstration using Python. The recursive least squares and least mean square filters are two widely used adaptive filtering algorithms. Each has its own strengths and weaknesses, and which one is preferable depends on the application. Below are the key advantages of RLS filters over LMS. First, RLS filter typically converge much faster than LMS filters, especially in situations where the input data is highly correlated or when rapid changes in the signal need to be tracked. The RLS algorithm minimizes the errors in the least square sense over all the past data, allowing it to adjust to changes in the signal more rapidly. Secondly, it has a better performance in non-stationary environment. These filters can adapt more quickly to non-stationary signals, that is, signals whose statistical properties are changing over time. This makes them more suitable for real-time applications where the environment or the signal being filtered is changing rapidly. For example, radar tracking or financial time series. Third is the optimal weight calculation. RLS filters attempt to find the optimal filter weights by minimizing the sum of squared errors over all past data, making them optimal in a least square sense. This means RLS filters provide a more accurate estimate of the filter weights compared to LMS, especially when the system dynamics are changing. Fourthly, it can handle correlated data. RLS filters handle correlated input data better than LMS filters. Since RLS uses an inverse covariance matrix to track the correlation between input signals, it can more effectively adjust in the presence of correlated data. Fifthly, it does not have any step size, which is a drawback in LMS filter, because if this step size is not correctly chosen, the LMS filter can become unstable. No such problem with RLS filters. And lastly, it has much better and steady performance in comparison to LMS filters. This tutorial is structured into 5 comprehensive parts, each addressing a key aspect of the RLS algorithm. In part 1, the section introduces the core differences between batch and recursive approaches in adaptive filtering. In part 2, the forgetting factor, which is a crucial concept in RLS that controls how the filter weights recent data against older data, is explained. Then the next 2 parts explain the RLS algorithm, and the 5th part is the summary of the algorithm, and the key concepts will be demonstrated using Python demonstration. So in this section, we'll try to understand the difference between batch processing and recursive processing. And we are going to take an example to explain this concept. And the example is that we are going to take a running series of numbers, say xi, so which is evolving like this, 1, 2, 3, 4, and so on and so forth till the nth term. And our objective is to calculate the mean or the average of this series. So this is the objective. And this series is unfolding in a serial fashion, in a sequential fashion. So let's first try to understand how batch processing addresses this problem. So in batch processing, what happens is that, let's say there are already 2 numbers in the series, that is number 1 and number 2. So what's the mean here? The mean will be 1 plus 2, the addition of 2 numbers, and total number of numbers in the series, that is 2. So here it is 3 divided by 2, which is 1.5. At this point, so suppose this is happening at time t1. At time t2, a new number appears in the series, which is number 3. And now we are required to calculate the mean again. So what we are going to do is, we are going to again add these 3 numbers and divide them by total number of terms. And this becomes 3 plus 2, 5, plus 1, 6, divided by 3. The new mean becomes 2. At this point, again, another number appears in the series, let's say 4. So we have to again recalculate everything. So we do 1 plus 2 plus 3 plus 4, and now divide by total number of terms in the series. And this turns out to be 2.5, and this is what is happening at time t3. So you can see 2 phenomena unfold here. One has implication on the memory. So if you see, at time t3, we should have saved all these numbers in the memory to do this computation. So as the time series is progressing in time, the memory requirement will continue to grow. So memory requirement is growing continuously as the time series is expanding. So it has implication on memory. The next part is the implication on computation. So as you can see, in the second mean, that is at time t2, we are adding these two numbers. But in the previous step, we had already added these two numbers. So there's a repetition of computation. And with each clock tick, the number of add operations are increasing. So here there are 3, before that there were 2, and before that there was 1. So as the series continue to grow, our computation requirement will also grow continuously. And this is not good, because if you are designing some kind of real-time system, then both memory and computation are at premium, and we must do something to save them. Now let's readdress the same problem, but now we are going to use recursive processing. And we are going to use symbolic math to solve this problem. So let's say we have series x times series x, and we need to calculate its mean. Mean is denoted by this line on top of x. And what we are basically doing is we are adding all the terms in the series. So this sigma represents that. And our terms are going from the first term till the last term. Let's say the last term is nth term. And we are adding all these terms till the end. And then we are going to weight this entire expression with 1 by n. So this is what is the classical definition of mean. And I'm going to just do some manipulation. I'm going to take this n and shift it here. So it becomes this expression, which is equally valid. And let me call it equation 2. So here we are talking about, in these two equations, we are talking about from first term to nth term. Let me take one step backward, and let me just talk about the same formulas, but instead of going from 1 to n, we will go to 1 to n minus 1 terms. So everything remains the same. We have to calculate the mean till n minus 1 terms. So my mean is represented like this till n minus 1 terms. And we have to add all the terms from first till n minus 1. So this expression captures that. And then we have to weight this expression with the total number of terms in the series, which are n minus 1. So this is the expression. Let's call it equation 3. And again, I'm going to do similar manipulation as I did earlier. I'm going to take this n minus 1 and shift it here. So this whole expression then becomes let me call it equation 4. So far so good. So let's move further. Let's start with this equation, equation 2. And I can rewrite this equation like this. So basically I'm doing summation from the first term till the nth term, which can also be written as summation till n minus 1 terms plus the nth term. So what does that mean? Essentially, this means that I'm doing summation from 1 to n minus 1, x and xi. And then to this I'm adding the nth term. And what is the nth term? xn. So this is equivalent, is equal to this expression. And notice something very carefully. Notice this part, which is exactly similar as this part. So we can actually take this expression and plug it here. So xn minus 1 mean multiplied by n minus 1 plus xn is nothing but xn mean multiplied by n. And I'm going to expand this now. So this becomes n x minus 1 mean plus minus xn minus 1 mean plus xn. So I've basically clubbed these two terms together, and this is equivalent to this. Now I'm going to divide both the sides, with n. So what happens if I do that? Let me just rearrange these terms. So this will become. So something very interesting happens here. This gets cancelled out. And what remains is this. Now, this is a very important expression because this is exactly what we are looking for. This is the recursive form, and we call it equation 5. And for a moment, let's just analyze what's happening. Let's analyze each and every term. So let's start with this. This is nothing but old mean, and it repeats here. So this is also old mean. And at this point, at some point, this new data becomes available. So this is nothing but new data sample. And this whole expression is nothing but is acting like a coefficient or a weight. And when we compute this expression on the right hand side, what we get is the new mean. So this is a very convenient form, and I'll explain why. So let's once again evaluate this expression from memory part and then computation part perspective. So let's see memory. I need to save some elements here. So the first term that I have to save is my old mean. Then at some point of time, new data becomes available. So my old mean is x n minus 1. New data becomes available. So I have to save it somewhere. This is my new data. Then I have a coefficient, which is data point 3. That coefficient I have to save somewhere, which is this. And then finally I have to save my new mean. Which is this. So in total, my memory requirement is just 4 locations. And this is independent of how this time series is growing. This time series might have hundreds and thousands of numbers, but in my memory, I just need to save 4 locations to process this equation. So this is a great reduction as far as memory is concerned. Now let's also talk about the computation. If you see carefully, there's one add operation, there is one subtract operation, which is negative add, and there is one multiply operation here, and there's a divide operation. So we have add, and I'll include subtract in this. So 2 operations. We have one multiply, and we have one divide. Now there are only 4 math operations. Now this is independent of how many number of elements are there in the series or how fast or slow it is growing. So there's an upper cap on the computation, which is very good because our resources are not going to run out, and there's an upper cap on the memory also, which means we are not going to run out of memory. So now if you are implementing any real-time system, solving the or formulating the problem in this manner saves both the memory and the computation. And this is basically the essence of recursive least square filters, which reduces the problem into the recursive form. So just as a last sanity check, if we continue with our series, we were 1, 2, 3, 4, and at some point number 5 appears. Up till this point, my old mean was 2.5, 4 plus 3, 7 plus, yes, it was 2.5. And now I'll just plug these numbers. So this is my new number. This is my old mean. And total number of numbers now, n is equal to 5. So as per recursive formula, new mean is equal to old mean into minus plus coefficient multiplied by this term. And one thing that you actually see here, which I forgot to mention earlier, if you see this entire expression in this bracket, this is nothing but an error term. Essentially, when the new number appears, new data point appears, this expression is subtracting it from the old mean. Basically, it's trying to find out how far the new data point is from the old average. And that distance is basically error, which is then weighted by this coefficient to correct this new mean. So this is nothing but error. Let's plug all the numbers here. So old mean was 2.5. Total numbers, coefficient is now 5 numbers. My new data is nth term, which is 5. My old mean is 2.5. And let's calculate this. This whole expression is 2.5. When divided by 5, this whole expression will become 0.5. And when I add 0.5 with 2.5, it will become 3. So this is my new mean. And this is done through recursive form. And if we do it the batch processing way, it will be this. which is 10 plus 5, 15. 15 divided by 5 is equal to 3. So both these results, they match. This was a sanity check for the formula. And by reducing the problem in recursive form, we've been able to save on computation, we've been able to save on memory. And this is basically the essence of recursive least filtering.